the statistical mechanics part 2. Okay, so here today we will discuss the derivation of Boltzmann distribution. So in equation 4.1, we have already studied that weight of a configuration depends upon the values of all the ni. So now, so let us see. The equation 4.1. So this is 4.1. So weight is equal to W equal to n factorial divided by n0 factorial into n1 factorial into n2 factorial into n3 factorial and so on. That means the weight of the configuration depends upon the ni values. So to determine the dominating configuration, we need to find the value of ni that maximize the function W. This can be achieved by varying the values of ni. So that means in order to determine the dominating configuration, that means which configuration will be highest population. So we have to maximize the weight function. We have to maximize the function weight function W. This can be achieved by varying the values of ni and looking for the value that corresponds to dw equals to 0. And again, you should remember that in the earlier classes, to determine the maxima of a function, we have to equate its first derivative to 0. So in order to find out the maxima of a function, we should take the first derivative to 0. So in order to find the maximum value of the weight function W, we should consider dw equals to 0. However, in case of system in many particles, it is mathematically convenient to maximize the function ln W instead of W. So here, as here the system contains a large number of particles, so we should take ln W instead of W, because firstly, for the large values of n, the value of W will be very large, and secondly, for ln W, we can employ Stirling's approximation that we have already discussed in the last class. So this is ln W. ln W. So this equation. So if you take logarithm, natural logarithm, both sides of equation 4.1. Now again coming to 4.1. So the equation 4.1 is like this. You can see this is equation 4.1. So the equation 4.1 tells that weight of the configuration W equals to n factorial divided by n0 factorial into n1 factorial into n2 factorial into n3 factorial and so on. n0 factorial into n1 factorial into n2 factorial into n3 factorial and so on. So solving this uh, uh, applying Stirling's approximation, and finally that will become equal to ln n factorial minus ln n0 factorial minus ln n1 factorial minus ln n2 factorial. Now putting the ln ni values together, so this equation 4.5 can be written as ln w equal to ln n factorial minus summation of ln I ln ni factorial. Now using Stirling's approximation in the above equation, we can write ln w. So here we will apply the Stirling's approximation of the on the right hand side of the equation 4.6. So we can write ln w equals to, first we will apply the Stirling's approximation here. Ln n factorial equals to n ln n minus n according to Stirling's approximation. And similarly, again we will apply here ln ni factorial equals to ni ln ni minus ni. Now the summation of ni equals to n, and hence we can write ln w equals to n ln n minus n plus, so this one summation of ni equals to n. So for this value we will put n minus ni ln ni summation of ln. So here this is summation of this one, summation of ni equals to n, and here you can see minus of minus, that will become plus, minus of minus, that will become plus. So here we will put n, and after that we will write this value. So this value is nothing but summation of ni ln ni. Now minus n plus n will be cancelled out. So we will write ln w equals to n ln n minus summation of ni ln ni. So let us note a change in the configuration of a system that is accompanied by change in population of each state from I to ni, from I to summation of each state I, from ni to ni plus dni. That means there will be a small change in every state I. So the change will be ni to ni plus dni. And the corresponding change in ln w can be given as, so the left hand side there will be small change, that is dln w equals to summation of del ln w divided by del ni dni equal to 0. So the term on the RHS gives the summation of the rate of change of ln w with ni multiplied by total change, this one. For w to be maximum, this summation must be equal to 0. In order to get the maximum value, the first derivative term should be equal to 0. So this summation will be equal to 0. So far we have considered all the states to have the same energy, implying that the configuration have the same total energy. Let us extend the argument now to different states having, so let us consider the different states having different energies. The first state having energy epsilon 0, second state having energy epsilon 1, then epsilon 2, and so on. Since an isolated system has a constant total amount of energy, so we can retain only those configurations that have the total energy. So the configuration must satisfy the following condition. That means summation of number of particles ni into energy state of each particle equals to total energy E. In other words, one particle in the collection is free to gain or lose energy, but the corresponding amount of energy must be decreased elsewhere in the system. And hence, thus the following condition should be hold. That means if there will be change in number of particles, so summation of epsilon I dni, that must be equals to 0. So this is equation 4.11. Now comparing equation 4.11 and 4.10, comparing both these equations that represent energy constraint on the system. Now since the total number of particles of the system are fixed, we cannot vary the population of all the energy state independently. A change in population of any state must be accompanied by corresponding changes in the population of the other state. As the total number of particles in the system is fixed, so if the population of any state will be increased, definitely the population of some other state must be decreased. And mathematically, summation of ni equals to n. It demands that the sum of all the changes in the dni must be 0. So that is summation of dni equals to 0. So now uh, equation 12 and 13, so these are the two equations comparing. So the equation 12 and 13 represent the number of constraint of the system. Thus the problem reduced to solving the equation 4.9 under the constraint are given in equation 4.11 and 4.13. For this we see the Lagrange method to understand the multiple to understand the multipliers. And here the Lagrange method, we should not discuss the derivation of the Lagrange method. So only we will apply this method to solve the problem. So for this, we rewrite the equation 4.8 by labeling the state j in place of I. So here the just we have changed the equation 4.8. So here we have labeled the I as j. So the equation 4.8 can be written as ln w equals to n ln n minus summation of nj ln nj. So differentiating this equation with respect to ni. Now we will differentiate this equation with respect to ni. So the left hand side of this equation will become dln w by dni equals to the right hand side will become dn ln n divided by dni minus summation of nj ln nj divided by dni. And solving the right hand side of the differential equation by using differentiation by parts. So this is the solution of this equation. And after that we know that n equals to total number of particles equals to n. So n equals to n0 plus n1 plus n2 up to dot dot ni. And since nj is independent of ni, we can differentiate the equation 17 with respect to ni, and the derivative of the ith term of the right hand side of this equation will be unity, whereas all other terms, that is the j terms, it will vanish. So that's why, so if we take differentiation of this equation with respect to ni, only this term will become 1 and the remaining term will vanish. So the overall equation will become dnj divided by dni equals to delta ij, whereas where the delta ij equals to 1 when I equals to j, and delta ij equals to 0 when I is not equal to 0. That means dn divided by dni equals to 1 when I equals to j. And again we can write, just write this, so rewrite this equation dln n divided by dni equals to 1 by n. Just we have multiply, just we have taken the derivative. So d ln n by dni equals to 1 by n. And again, and if we put same principle here, we can write d ln n j divided by dni equals to 1 by nj dn j divided by dni. So this is solve this equation. So you have to simplify that one. After simplifying, we will get, so the final. I am coming to the final part. So simplifying this equation, we can write taking and after taking logarithm, we can write ni equals to n e to the power alpha into e to the power minus beta epsilon j. So this equation is the mathematical form of Boltzmann distribution. It gives the number of molecules in the ith energy state of the dominant configuration. So this is one long question. That means 5 marks question. So if there will be derivation of the Boltzmann distribution, so this is the final mathematical form of the Boltzmann distribution. And after that, some additional questions will be there. Determination of the value of alpha. We know that some of the populations of the ni So here we will determine the value of alpha in this equation in this Boltzmann distribution. So we know that sum of the population Ni of the states is equals to total number of molecules n. That means summation of Ni equals to n. And again using equation 35 and substituting the value of Ni, this one is equation 35. So here if we put the value of Ni, substituting the value of Ni, we can write summation of n e to the power alpha into e to the power minus beta epsilon j equals to n. Now simplifying and cancelling n both sides, we can write this one n e to the power alpha into summation of e to the power minus beta e epsilon j equals to n, and after that again simplifying we can write e to the power alpha into summation of e to the power minus beta epsilon j equal to 1, and imply that e to the power alpha equals to 1 by summation of e to the power minus beta. So the term in the denominator is called partition function and is represented as q. So here this one can be represented as q. So the denominator is known as the partition function and that can be represented as q function. We can finally we can get the value of alpha, and the pending the determinant on 4.35 using partition function in this equation. Yes, this one using partition function in this equation 35, we can write. We find that the probability pi of the occupying a given energy level I, that will become pi equals to ni by n. So that is equal to e to the power alpha into e to the power minus beta epsilon j. So which is equal to e to the power minus beta epsilon j divided by q, and this is equation 40. So the equation 40 is an important result. It quantifies the probability of occupying given energy of a dominant configuration of energy. This well known, and equation 40 to the expression of probability involving the discrete variables. So if we'll compare equation 40 with the probability factor, we find the Boltzmann distribution is nothing more than the statement of probability. So the Boltzmann distribution is just the statement of probability. And in the similar way, we can find out the, so this is another part, that is determination of the value beta. So here, solving this equation just like in the similar way, we can find out the value of beta. So small k is nothing but that is called a Boltzmann constant, and having the value 1.38 into 10 to the power minus 23 joule per Kelvin. Now, the Boltzmann equation 40, whatever we have discussed, that can be rewritten as Ni equals to n by q into e to the power minus epsilon I divided by kt. Now, the denominator of this equation 61, this is 61, is termed as particle partition function or molecular partition function, and it is represented as q. It is one of the most important quantity in the statistical thermodynamics and will be taken up in details in the next section. So here, so partition function will be another long question, so that we'll discuss here. Now we can write this equation 61 can be like this: Ni equals to n into e to the power minus epsilon I divided by kt whole divided by summation of e to the power minus epsilon I by kt. So this is the mathematical expression of Boltzmann distribution law, and signifies that if the energy associated with some state or condition of the system is epsilon, then the frequency with which the state or condition occurs, or the probability or its occurrence, is proportional to e to the power minus epsilon by kt, where T is the system's absolute temperature and small k is the Boltzmann constant. Now coming to one question. Most probably from this portion, numerical questions will come. A molecule can be any of the two states. Its excited state is separated from the ground state by this much amount of energy, that is 8 into 10 to the power minus 21 joule amount of energy. And if the ground state has the energy 0, calculate the fraction of the molecule in the excited state at 300 Kelvin. So this is your numerical question. So in order to solve this question, we have to put the Boltzmann distribution law. Now according to the Boltzmann's law, Ni divided by N equals to e to the power minus epsilon I by Kt whole divided by summation of e to the power minus epsilon I by Kt. Now let us first calculate the denominator by substituting the exponents. So first we will solve this value, and after that we will put this value, and then we will find out the fraction of molecules present in the excited state at 300 Kelvin. So first we will solve the value of the denominator. So the denominator can be solved by substituting the value. So here the denominator is nothing but summation of e to the power minus epsilon I Kt, which is equals to e to the power 0 plus e to the power minus epsilon 1 by Kt, which is equals to, so why that is 1? Because you are here we are considering the first excited state, and the ground state, for the ground state we are putting the value of 0. So for ground state the value will become 0, so that's why that is e to the power 0. And for the first excited state it is e to the power minus epsilon 1 by Kt, and the difference value, the energy difference. So according to the question, the energy difference is there, and here the ground state having the energy 0. So putting the value of energy 0 here, we will write e to the power 0 plus, and after that in the first excited state the energy is 8 into 10 to the power minus 21 joule. So in the second term, so e to the power 0 is 1. So in the second term, we will write e to the power minus. In place of epsilon 1, we will put this value 8.0 into 10 to the power minus 21 joule. And in the denominator, we will put the Boltzmann constant value. And for temperature, we will put 300. Now, solving this, so this type of question can be solved by using scientific calculator. Now solving this, we can write summation of e to the power minus epsilon 0 by Kt equals to 1 plus e to the power this value, which is equal to 1 plus e to the, so solving total this value will be minus 1.931, and this value can be solved using scientific calculator. Directly the value will show, so the value will be 0.145, and hence the total value will become 1.145. Now coming to the fraction of the molecules in the excited state can be calculated as n by, so here we have just calculated the value of denominator. So the denominator value is 1.145, and after that the fraction of molecules in the excited by n equal to this one, e to the power minus epsilon I by Kt. So here we are putting e to the power minus, in place of epsilon I, we are taking the value 8.0 into 10 to the power minus 21 joule, and in place of K, we are taking the Boltzmann's constant, and for T, we are taking 300 Kelvin. Now again solving this, we can write So that is equal to 0.145 divided by 1.145, that is equal to 0. Will be 0.127, that is only percent upcoming semiconductor examination. So this equation
Sir, your
62,
voice
this
is
one,
breaking, sir.
this equation 62 gives the population of the ith level with respect to of the ground state. The ith level may be first excited state, maybe second. Okay. So now we'll discuss the molecular partition function. So in the molecular partition function, you will see three different long questions are there. So for so in the beginning of this of the unit, we stated that the statistical thermodynamics act as the bridge between the molecular properties and the ball properties. In the initially we have discussed that the statistical thermodynamics acts as a bridge for the molecular properties. Molecular properties means microscopic properties like bond length, bond energy, nuclear energy, whatever may be. So that is in the atomic or molecular level, and it will act as a bridge between the molecular properties and bulk properties of the microscopic system. And the partition function is the tool that relate to the property of the molecule of the microscopic properties of the system. Molecule that relate to the property of the molecule to the macroscopic property of the system. As discussed above, the partition function in the just in the previous section we have discussed that Q is the partition function which is equals to summation of e to the power minus epsilon I kt. Summation of e to the power minus epsilon I divided by kt. This gives the sum over all the energy states in the Boltzmann distribution. Now you should again remember that the Boltzmann distribution gives the distribution of molecule over different energy levels in the dominant configuration. Therefore, the partition function is known as molecular partition function. So while considering the Boltzmann distribution, we have to assume that the degeneracy of all the energy level is 1. However, since the molecules have many degeneracy energy levels, degeneracy means there will be multiple states in a particular energy level. So initially we have assumed that for every energy level, the degeneracy will be 1. That means single state will be there. But in the actual case, the molecules have many degenerate energy levels. So it is important to include the degeneracy in the expression of the partition function. So that's why putting the value of the degeneracy, the partition function can be modified as Q equals to summation of Gi into e to the power minus epsilon I whole divided by kt. So here this is the partition function, but initially we have considered that the degeneracy of every energy level should be 1. But in the actual case, the molecules have many degeneracy are possible, and the degeneracy will be Gi. Now including the degeneracy in the molecular partition function, the molecular partition function can be written as Q equals to summation of Gi into e to the power minus epsilon I divided by kt, and here Gi is the degeneracy of the ith energy level. Now until now we have discussed the total energy of a molecule for a given energy state. Now you know that the total energy of the molecule has the contribution from the translational energy, also from the rotational energy, from the vibrational energy, and from the electronic energy level of the molecule. So till now we have discussed about the total energy of the molecule, but again we know that the total energy of the molecule has different contribution. So the total energy of the molecule is the summation of translational energy, rotational energy, vibrational energy, and electronic energy. So that is epsilon I total. So this is the total energy of the molecule. Epsilon I total equals to epsilon I translational energy, epsilon I rotational, epsilon I vibrational, epsilon I electronics. And again, according to the Born of Oppenheimer approximation, these energies can be taken as independent of each other. Thus, that means the translational energy and the rotational energy, vibrational and electronic energy, all the different contribution of energies are independent upon each other. Thus, the molecular partition function without considering the degeneracy can be written like this. So in place of the total energy, we are writing this one. So here we are considering uh, without considering the degeneracy. That means the degeneracy should be 1. When you consider the degeneracy should be 1, then the molecular partition function can be written as Q equals of e to the power minus epsilon I translational plus epsilon I rotational plus epsilon I vibrational plus epsilon I electronics divided by kt. That means in place of epsilon I, we are writing this value. In place of epsilon I, we are writing the summation of all these values. And again, that can be written as Q equals to and all the values that are independent of one another, and hence Q equals to summation of e to the power minus epsilon I translational by into e to the power minus epsilon I rotational by minus by. Now separating each term and introducing the degeneracy I translational Okay, so here thus the total partition function is the product of partition function of each type of energy of the molecule, and this is known as factorization of partition function. Now we can calculate the contribution of each type of partition function of the. Just wait 1 second. Okay, here, so we will find out the individual partition functions. So there will be four type of partition functions will be there. That is translational partition function, rotational partition function, vibrational partition function, and electronic partition function. All the four types of partition functions are four. So individually we will calculate. So individually that will be one question, and definitely and most important one questions, because in the previous year question in the general thermodynamics. So there will be question from most of the questions came from the general thermodynamics or classical thermodynamics. So definitely for this year or for the coming year, questions will be from the statistical thermodynamics and particularly from this partition function. So here you can see, first we'll discuss the translational partition functions. You know that the translational energy has three components, because the translational energy related to the energy of the particle due to motion of the particle in the three-dimensional axis. So the translational energy has three components, one each in the x and y and z directions. Each of these contribution to the translational partition function. To work out the expression, we will consider the motion of the particle in only one dimension, so that if we find the if we consider the motion of the particle in one axis or one direction, and after that if we determine the value of the translational partition function, similarly the translational partition function from the y axis or the y direction, and similarly from the z direction. So here only we will consider the motion of the particle in one dimension box system, and the for the motion of the particle in one dimensional box system you have already studied in your graduation level from quantum mechanics. So that is En translational equals to n square h square divided by 8 ml square. Again I am telling, epsilon n translational equals to n square h square divided by 8 ml square. You recall the particle of mass m confined in a one-dimensional box of length L, then the energy of the particle will be given as, then the translational energy of the particle will be given as epsilon n translational equals to n square h square divided by 8 ml square. So m is the mass of the particle, L is the length of the one-dimensional box, h is Planck's constant, and n is the quantum numbers. That means the number of the different energy levels. So the value of the n will be 1 or 2 or 3 and so on. Hence here n is the quantum number, the energy of the lowest energy state n equals to 1, and for the lowest energy state the translational energy will be obtained by putting the value of n equals to 1 in this equation 74. By putting the value of n equals to 1, we can write epsilon n translational equals to h square divided by 8 ml square. Now, in case of Boltzmann distribution, the energy of the lowest energy level is taken as 0. Therefore, the energy of the nth energy level must be scaled relative to the lowest energy level. It is implied that the energy of the nth energy level relative to the lowest energy level is equals to, so that is En translational equals to, so the energy of the nth energy level, so this one is the energy of the nth energy level, n square h square divided by 8 ml square, and this is the energy of the lowest energy level, h square by 8 ml square. So the energy of the nth energy level relative to the lowest energy level is equals to epsilon n translational equals to n square minus 1 epsilon 1 translational. That is, the translational partition function in the x direction can thus be written as q translational equals to summation of e to the power minus n square minus e to the power minus n square minus 1 into epsilon 1 translational. So that means in place of this we are putting these values divided by kt. So this is the translational partition function along x direction, and the summation over all the energy levels. So if we consider for all the energy levels, since the translational energy levels are very close to each other, they can be taken as very continuously. Hence we replace the summation by integration. So uh, uh, so why here we are taking integration because in the translational energy levels are very close to one another. That means the translational energy levels are in a continuous format. So the Qx translational equals to integration of e to the power minus n square minus 1 epsilon 1 translational divided by kt dn, and the integration will be taken from 1 to infinite. Now solving this integral, we use the approximation that, so in order to solve this integral, we will use the approximation that n square minus 1 should be similar to n square, because the value of the n will be very high. So the n square minus 1 is approximately equal to n square, and the lower limit of the integral should be changed to 0. Therefore, Qx translational will be integration from 0 to infinite integration of e to the power minus n square epsilon 1 divided by kt dn. Now let us substitute these values to be x square. That means in order to solve this integration, we should consider these values as x square. So after taking these values will be x square, and differentiating and simplifying, we will get dn equals to kt divided by, so here we are taking this value as x square, and after solving that and differentiating and simplifying, we can write it dn equals to kt divided by epsilon x translational. So here this is in place of here we are putting x, so this is epsilon x translational whole to the power 1 by 2 dx. Now substituting in equation 79, substituting this value in equation 79. So this is just the solution by different steps. Qx translational equals to kt divided by epsilon x translational to the power 1 by 2 into integration from 0 to infinite e to the power minus x square dx. Now the integral here, that is the standard form of the integral, integration of e to the power minus x square dx, which is equals to, and its value is equal to pi to the power half divided by 2. Now substituting this value, we can write the translational partition function along the x-axis, that is qx translational equals to kt divided by epsilon x translational to the power half into pi to the power half divided by 2. Now substituting this expression for the epsilon x translational from equation 74 in equation 83, we can write, so this is equation 74. Yes. This value, equation 74, this is epsilon n translational. Now putting the value of equation 74 in equation 83, we can write qx translational equals to kt 8 ml square by h square to the power half into pi to the power half by 2. Now again on simplification, the value for the translational partition function along the x-axis qx translational equals to 2 pi ktm divided by h square whole to the power half into L. Translational partition function along x-axis, along only one dimension, that is along x-axis, and if we want to find into y translational into qz translational. So already we have solved this value, and similarly the value of qy translational will be like this. So this is the value of qx translational, and for qy translational the value will be like this, and for qz translational the value will be this one, and simplifying we will write q translational. So just we have to, so we have solved the value for one axis, and similarly we will put all the values for the y axis and for the z axis. Let the length of the particle in the y axis will be b, and length of the particle in the z axis will be h. So simplifying this, we can write q translational equals to 2 pi kTm by h square whole into 3 by 2 lbh. So here lbh, L is the length of the particle, length traveled by the particle along x-axis, that is L, and B is the length traveled by the particle along y-axis, and H is the length traveled by the particle along z-axis. So LBH value is nothing but volume. So in place of LBH, we can put V, and hence the total translational partition function Q translational equal to 2 pi kTm by h square whole to the power 3 by 2 into V. So this is the final derivation of the translational partition function. So this is one long question. Starting from here, we will continue, and finally we have to derive this one. So this is one long question. And now coming to one numerical question. So the numerical question, let us see the numerical question. 1 mole of neon gas. We know that the molecular mass of the neon gas is 20.1797 gram per mole. So here gas is this one. Occupies a volume of 0.0245 meter cube at 298 Kelvin. Calculate the translational partition function for the system. Again, the question will be like this. So here first we have derived the value of the translational partition function. This is one long question. And after that some additional numerical question will be there. 1 mole of the neon gas having molecular. We know that the molecular mass of the neon is this one, 20.1797 gram per mole. That occupies a volume of 0.0245 meter cube at 298 Kelvin. Calculate the translational partition function for the system. And here we have already solved, and first you should know how to derive the translational partition function, and again you should remember the final expression for the translational partition function, because if only numerical question will come, then we should put the final derivation or final equation of the translational partition function. So the translational partition function is given by the following expression. So this expression also you have to remember, that is Q translational So the translational partition function, that is Q translational, equals to 2 pi kTm divided by h square to the power 3 by 2 into V. Now most of the parameters are given or known. However, we need to calculate the value mass of one neon atom to use this expression. Here the molecular mass of neon is there, but we have to calculate the mass of a single neon atom. So the mass of a single neon atom equal to molecular mass divided by Avogadro number. So molecular mass means that is the mass of Avogadro number of neon atoms. If we want to find out the mass of a single neon atom, so that will become molecular mass by Avogadro's number. So here molecular mass, here it is given the molecular mass is 20.1797 gram per mole, and here we are putting the value in kilogram. So that will become 0.02019797 kilogram per mole. Hello, Mr. Pramod Kumar. Hello, Pramod Kumar. You should mute. You please mute. So here we have to find out the mass of a single neon particle. So the mass of a single neon atom. So that is molecular mass divided by Avogadro's number. Here the molecular mass given in the question, the molecular mass is 20.1797 gram per mole. But here we are putting the value in kilogram per mole. So here the molecular mass of neon atom in kilogram per mole divided by Avogadro's number, that is 6.022 into 10 to the power 23, and the finally so this is the mass of a single neon atom, that is 3.351 into 10 to the power minus 26 kg. Now, so here we will find out the value of translational partition function. Q translational equals to this. So here we are putting 2. After that the value of pi. After that the value of K. K means Boltzmann constant. And after that the value of temperature. Temperature here it is given in the question, that is 298 Kelvin. And after that mass of the neon atom. So here we have calculated the mass of the neon atom. This one divided by h square. H is nothing but the Planck's constant. Planck's constant is 6.626 into 10 to the power minus 34 joule second, and its whole square into volume. So here in the question the volume is given as 0.0245 meter cube. So all the values are given. Just we have calculated the value of a single neon atom, and after putting all the values in the expression for the translational partition function, we can find the value of the translational partition function Q translational equals to 2.148 into 10 to the power 24. So this is one long question and it's numerical question. So in your semester examination, you may face derivation of this expression or numerical questions like this. So these are very easy. So first you should prepare for the derivation of this expression, and again you should remember that one, because if numerical question will come, you have to directly put that expression for the translational partition function, and after that you will put the respective values, and then you have to solve. Now coming to the next partition function, that is called a rotational partition function. So here exactly in the similar way, Q rotational, that is rotational partition function, equals to summation of GI rotational into e to the power minus epsilon I rotational by KT. Now recall from the again from the so here 2, 0, 1, 2, these are the rotational quantum numbers. Just like translational quantum number, here J equals to rotational quantum number. The rotational quantum number value may be 0, maybe 1, maybe 2, and so on. And h cross is h by 2, and I is the moment of inertia of the particle. Since the lowest rotational energy level is 0, no need to scale EI rotational with respect to lowest energy level. Further, again you know that the degeneracy of the again we know from the graduation level that the degeneracy G, the degeneracy of the rotational energy level equals to 2J plus 1. So in place of G we should write it 2J plus 1, and hence the rotational partition function value will become Q rotational equals to summation of 2J plus 1 into exponent means e to the power same thing. Exponent means e to the power. So exponent of minus. So here we are putting the value rotational quantum epsilon I rotational in place of epsilon I rotational we are putting this value divided by k. And simplifying, we are writing the expression. So simplifying the above expression expression, we can find Q rotational equal to summation to j plus 1 into exponent of minus j into j plus 1 h cross square divided by 2 I k t. You may note that all are constant x and j. So here j is one variable and t is variable. The remaining parts are constant. So in the above expression, so the constant is called rotational temperature. So the constant that can be so written as equal to summation of 2j plus 1 e to the power minus small is small because the temperature is more larger than energy, and replace the summation q rotational equal to integration plus 1 theta r by t dj. Solving integration is not straightforward quantum number appears in the body as well as in the exponent part of the integral. Yes. So this is so here we have derived the another long question, that is the value of rotational partition function q rotational equals to 8 pi square IKT divided by h square. So this is another derivation. Again, you have to practice this long question and numerical questions also there. Now coming to the third partition function, that is called vibrational partition function. Again, we are putting q vibrational equal to summation of gi vibrational into e to the power minus epsilon I vibrational by kt. And again, From the graduation level in the from molecular spectroscopy, we know that epsilon vibrational equals to nu plus half h nu, where nu is the vibrational frequency, vibrational and so nu is the vibrational quantum number, nu equal to 0, 1, 2, 3, and the energy levels are singly degenerate, and the lowest energy level, the energy of the lowest energy level here, that is not zero, that is called zero point energy. So the value is epsilon 0 equals to half h nu, that we have studied from the graduation level from molecular spectroscopy. And the difference between the two conjugative energy level is h nu, and hence q vibrational equals to e to the power minus 0 plus half h nu by kt plus e to the power minus 1 plus half h nu by kt plus e to the power minus 2 plus half h nu by kt, and so on. Now simplifying this, we can write q vibrational equal to e to the power minus h nu by 2 kt plus e to the power minus 3 h nu by 2 kt plus e to the power minus 5 h nu by 2 kt. So this can be written as q vibrational equal to e to the power minus h nu by 2 kt 1 plus e to the power minus 3h nu by kt, and so on. So here if we put h nu by kt equal to x, we can rewrite the above this. And here the term in the bracket in the is written as, so this term in the bracket can be written as, can be solved as 1 by 1 minus e to the power minus x. Now putting substituting these values, we can write q vibrational equal to 1 by 1 minus e to the power minus h nu by kt equal to e to the power minus h nu by 2 kt whole divided by e to whole divided by 1 minus e to the power minus h nu by kt. And this expression, we have not scaled the energy of the upper level to epsilon 0. Thus this equation 94 include the 0 point energy. So this one, equation 94 is the include the 0 point energy. So this one, so putting this value of the 0 point energy, we can solve and find the q vibrational equals to the value of the vibrational partition function becomes q vibrational equal to 1 by 1 minus e to the power minus h nu by kt. Now coming to, so this is another derivation. Now coming to the electronic partition function. So here the electronic partition, the derivation of the electronic for the electronic partition function, we will again write q electronics equal to summation of gi electronics into e to the power minus epsilon I electronics by kt. So here one question is there in between that part, the energy of the different energy of the first three electronic states. So this is the energy of the first electronic state. The energy is 0 and having degeneracy 1. For the second electronic state, the energy is 3.26 into 10 to the power minus 22, having degeneracy 3. For the third energy state, the energy is 8.64 into 10 to the power minus 22, having degeneracy 5. Calculate the electronic partition function. So this is direct the value of the electronic partition function. No need to derive this one. Just we are putting this expression q electronics equal to summation of gi electronics into e to the power minus ei electronics by kt. Now for this question, q, so there is the second state, the gi value is 3. For the third state, the gi value is 5. So now q electronics equal to g1 electronics into e to the power minus epsilon 1 electrons by kt plus g2 electronics into e to the power minus epsilon 2 electronics by kt plus d3 electronics into e to the power minus epsilon 3 electronics by kt. Now let us first calculate the value of kt. So here kt means k is Boltzmann constant, and putting the value of T, that is 300 Kelvin given in this question, we can calculate the value of kt like this. So q electronics equal in place of GI1 we will put 1 because that is given in the question. Degeneracy for the first state is 1. Now e to the power minus epsilon 1 electronics by kT. So here for the first state the value in the question it is given epsilon 1 electronics value. According to the question you can write the value is given 0. So 0 by kT value, we have already solved the value of kT. So 4.413 into 10 to the power minus 21 joule plus the second state the degeneracy is 3. So here in place of G2 electronics we will put 3, and after that e to the power minus epsilon 2 electronics by kT. So here e to the power minus epsilon 2 value is given in the question, that is this one. This is the value of epsilon 2, and kT value we have solved, plus the third term is G3. G3 value is given in the question, that is 5, and its epsilon 3 value is there. Now putting all these values we can write Q electronics is like this. Now simplifying by using scientific calculator you can simplify that. So Q electronics equals to 1 into e to the power 0 plus 3 into e to the power minus 0.079 plus 5 into e to the power minus 0.029. Now again solving we can write Q electronics equal to 7.827. So the electronic partition function would be like this. So exactly this question may come or some similar type of question, but the methods will be same. Now coming to the next part, that is called canonical ensemble. Ensemble, canonical ensemble. So what is canonical ensemble? So we have discussed. So here we'll take 2-3 minutes of break. After that again we will start.
Okay, sir.
Okay, so we'll continue. So here we'll discuss what is canonical ensemble. We have discussed in the statistical treatment of a single system, which is the collection of many identical particles. A system is also known as assembly. A group or collection of, again, the statistical treatment of a single system, which is collection of many identical particles, is a system is also known as assembly. Now, a group or collection of assemblies or system, collection of systems is known as assembly. So, I'm repeating this. The statistical treatment of a single system, which is a collection of many identical particles, is known as assembly. And again, a group or collection of assemblies or systems is known as ensemble. We had considered the total energy of the system to be fixed. However, in case of ensemble, the energy of the systems in contact with surrounding will fluctuate. So for assembly, the energy of the system may fixed, but for ensemble, the energy of the system which is in contact with the surrounding will fluctuate. Since different parts of the ensemble can also be exchange energy with each other, the energy of the ensemble will fluctuate. So, in such cases, we cannot assume that the energy is fixed. However, we can fix the temperature of the ensemble by keeping it in contact with a large heat reservoir. So, the word canonical means according to the rule, and the ensemble in which the rule in which by rule the number of molecule n, volume v, and the temperature T are kept constant is known as canonical ensemble. So in canonical ensemble, all the systems are at same temperature, same pressure, and same volume. Then the total energy of the canonical ensemble is constant. If the canonical ensemble in canonical ensemble, so the total energy of the ensemble is not constant. But canonical ensemble means the systems are in same temperature, same pressure, and same volume, and hence the total energy of the canonical ensemble is constant. However, the energy of the individual systems can be different. The energy of the individual systems will be close to the average energy of the ensemble. So in this section, we will extend the statistical treatment of a system into an ensemble. Now, let the particles in an ensemble is equal to n, and the number of particles in the ensemble with energy EI equals to Ni, and weight of the configuration of the ensemble with population N0, N1, N2, N3, etc. And hence, according to the Boltzmann, so if you apply the Boltzmann distribution, the canonical distribution of the dominant configuration of the ensemble with constant of the total energy of the ensemble E is constant and N is also fixed. So we can write the weight function W equals to Ni factorial, just similar type of derivation here for canonical distribution, and put beta Ei divided by Q. So here Q is the canonical function to canonical ensemble. Now this is the relationship partition function of the ith state. Here Q is the partition function of the canonical ensemble. Partition function of the first system Q1 function. So the average energy of the molecule epsilon equal to E by N. So here the third part over, that means the classical thermodynamics and statistical thermodynamics parts over, and you will go through all these questions given in your study material, and from next class you will appear for inorganic, and when one cycle will complete and if again class will be allotted, we will discuss the remaining part of the thermodynamics. Okay.
Yes, sir.
Hello.
Yes, sir. Yes, sir.
The block is completed from the next
Sir,
class.
one question.
Okay. Yes. Hello.
Yeah, sir. Yeah, yes, sir. One question, like if I may, sir.
Okay. You are.
Yeah. Yeah. So in the syllabus for semester 1, do you have block 1 or block 1, 2, 3, 4 as well?
No. For syllabus, all the blocks are there. So first one cycle, if one
Okay.
cycle will be completed, after that again
Okay.
we will start. So here block 1
Oh,
completed.
okay, sir.
After
Okay.
that
Thank you, sir.
inorganic classes will be there. Organic classes will be there. After completion of one cycle, again we will discuss that one.
Okay, sir. Thank you so much. Thank you, sir.
Okay. Okay. Okay.
Thank you, sir.